The nuclear theory of the atom. We shall now consider the second part of the foundation on which we shall build, namely the conclusions arrived at from experiments with the rays emitted by radioactive substances. I have previously here in the Physical Society had the opportunity of speaking of the scattering of alpha rays in passing through thin plates, and to mention how Rutherford, 1911, has proposed a theory for the structure of the atom in order to explain the remarkable and unexpected results of these experiments. I shall, therefore, only remind you that the characteristic feature of Rutherford's theory is the assumption of the existence of a positively charged nucleus inside the atom. A number of electrons are supposed to revolve in closed orbits around the nucleus, the number of these electrons being sufficient to neutralize the positive charge of the nucleus. The dimensions of the nucleus are supposed to be very small in comparison with the dimensions of the orbits of the electrons, and almost the entire mass of the atom is supposed to be concentrated in the nucleus. According to Rutherford's calculation, the positive charge of the nucleus corresponds to a number of electrons equal to about half the atomic weight. This number coincides approximately with the number of the particular atom in the periodic system, and it is therefore natural to assume that the number of electrons in the atom is exactly equal to this number. This hypothesis, which was first stated by van der Broek in 1912, opens the possibility of obtaining a simple explanation of the periodic system. This assumption is strongly confirmed by experiments on the elements of small atomic weight. In the first place, it is evident that according to Rutherford's theory, the alpha particle is the same as the nucleus of a helium atom. Since the alpha particle has a double positive charge, it follows immediately that a neutral helium atom contains 2 electrons. Further, the concordant results obtained from calculations based on experiments as different as the diffuse scattering of X-rays and the decrease in velocity of alpha rays in passing through matter render the conclusion extremely likely that a hydrogen atom contains only a single electron. This agrees most beautifully with the fact that J.J. Thomson in his well-known experiments on rays of positive electricity has never observed a hydrogen atom with more than a single positive charge, while all other elements investigated may have several charges. Let us now assume that a hydrogen atom simply consists of an electron revolving around a nucleus of equal and opposite charge, and of a mass which is very large in comparison with that of the electron. It is evident that this assumption may explain the peculiar position already referred to which hydrogen occupies among the elements, but it appears at the outset completely hopeless to attempt to explain anything at all of the special properties of hydrogen, still less its line spectrum, on the basis of considerations relating to such a simple system. Let us assume for the sake of brevity that the mass of the nucleus is infinitely large in proportion to that of the electron, and that the velocity of the electron is very small in comparison with that of light. If we now temporarily disregard the energy radiation, which, according to the ordinary electrodynamics, will accompany the accelerated motion of the electron, the latter, in accordance with Kepler's first law, will describe an ellipse with the nucleus in one of the foci, denoting the frequency of revolution by omega, and the major axis of the ellipsis by 2 times a. We find that omega squared is equal to the quotient where the numerator is 2 times w cubed divided by pi squared e to the 4 m, and 2a is equal to e squared over w, where e is the charge of the electron and m its mass, while big W is the work which must be added to the system in order to remove the electron to an infinite distance from the nucleus. These expressions are extremely simple, and they show that the magnitude of the frequency of revolution, as well as the length of the major axis, depend only on W, and are independent of the eccentricity of the orbit. By varying W, we may obtain all possible values for omega and 2a. This condition shows, however, that it is not possible to employ the above formulae directly in calculating the orbit of the electron in a hydrogen atom, For this, it will be necessary to assume that the orbit of the electron cannot take on all values, and in any event, the line spectrum clearly indicates that the oscillations of the electron cannot vary continuously between wide limits. The impossibility of making any progress with a simple system like the one considered here might have been foretold from a consideration of the dimensions involved. For with the aid of E and M alone, it is impossible to obtain a quantity which can be interpreted as a diameter of an atom or as a frequency. If we attempt to account for the radiation of energy in the manner required by the ordinary electrodynamics, it will only make matters worse. As a result of the radiation energy W would continually increase, and the above expression, equation 4, show that at the same time, the frequency of revolution of the system would increase and the dimensions of the orbit decrease. This process would not stop until the particles had approached so closely to one another that they no longer attracted each other. The quantity of energy which would be radiated away before this happened would be very great. If we were to treat these particles as geometric points, this energy would be infinitely great, and with the dimensions of the electrons as calculated from their mass, about 10 to the minus 13 centimeters, and of the nucleus as calculated by Rutherford, about 10 to the minus 12 centimeters. This energy would be many times greater than the energy changes with which we are familiar in ordinary atomic processes. It can be seen that it is impossible to employ Rutherford's atomic model so long as we confine ourselves exclusively to ordinary electrodynamics. But this is nothing more than might have been expected. As I have mentioned, we may consider it to be an established fact that it is impossible to obtain a satisfactory explanation of the experiments on temperature radiation with the aid of electrodynamics, no matter what atomic model be employed. The fact that the deficiencies of the atomic model we are considering stand out so plainly is therefore perhaps no serious drawback. Even though the defects of other atomic models are much better concealed, they must nevertheless be present and will be just as serious.